Welcome back to the Deep Dive. We're here to unpack the foundational ideas from cutting-edge AI research, really getting into the weeds for you, our expert listeners. Today, we're tackling something that's really become a central challenge for anyone building autonomous agents. How do we give these LLM-powered agents the ability to solve really complex, open-ended problems? The kind that needs serious, multi-step information seeking. We're talking about the core engine behind things like, deep research systems.
Yeah, and it's a specific kind of challenge, right? It's not just about making the LLM generate better text or recall facts more accurately. The real bottleneck, the limiting factor, is that information-seeking capability, IS, as they call it. An agent that's truly useful needs to be smart about navigating the web, changing its search approach on the fly, dealing with tons of messy information, and then, crucially, putting it all together into a correct, verifiable answer. And the thing is, no matter how big your base LLM is, its actual performance on these tasks, it's almost entirely dictated by the training data, specifically those trajectory examples you use for supervised fine-tuning in the RL phase.
Right, and that hits the core problem that, well, the whole research community has been wrestling with. Good, complex IS training data is just really hard to come by. It's scarce. And worse, the usual ways people try to make this data, synthesize it, they seem to have some fundamental flaws. The paper we're looking at today calls them information-driven. Can you maybe unpack what that means and why it's, well, problematic?
Sure. So this information-driven approach, and yeah, systems like WebDancer or TaskCraft fall into this category. They basically work backwards. They start by just grabbing a bunch of stuff from the web, following links, doing some initial searches, maybe somewhat randomly. They collect all this raw content, try to organize it a bit, and only then, after they have this pile of information, does an LLM try to generate a question and a reasoning process and an answer that, fits the facts they just gather.
Ah, okay, so the complexity is sort of reverse engineered. The reasoning has to fit whatever facts they happen to find.
Exactly. And that leads to a couple of really big issues. First, inconsistency. The LLM that's trying to generate the question, it often struggles, like really struggles, to fully grasp the structure of that pre-collected information, which is often huge, fragmented, maybe even contradictory. So you frequently get this mismatch, this inconsistency between the kind of reasoning steps you want the agent to learn and the information that's actually needed to solve the question it came up with. This often forces the LLM to just, make stuff up, hallucinate steps or connections, and the result is noisy data, structurally unsound data, not great for training robust agents.
Yeah, makes sense. And you mentioned a second limitation, something about diversity and hitting a ceiling.
Yeah, because that initial information gathering is often, let's say, unstructured or just follows obvious links. The training examples it produces tend to look pretty similar. Homogeneous, it hits a complexity ceiling pretty fast. You get the same kinds of information structures over and over again because it's basically limited by whatever was easy to find in that first trawl of the web. It just doesn't have the underlying structural guidance needed to create tasks that demand genuinely deep, multi-step compositional reasoning.
Okay, so that sets the stage perfectly for the big shift we're digging into today, WebShaper. This is a framework coming out of Alibaba Group, and they call it formalization-driven. It seems to completely flip that reactive process around.
It does. WebShaper is proactive, not reactive. Instead of starting with a bunch of web content, it starts by systematically, rigorously defining the complex requirements of the information-seeking task itself. And it does this using set theoretic constructs, formal mathematics. This formal structure then becomes the absolute blueprint, the non-negotiable guide for everything that follows. It guides how complexity is added, how information is searched for, and how the final result is validated. It's about injecting structural certainty right at the beginning of the agent training pipeline.
Got it. So for you listening, our mission today, as experts yourselves, is to really dissect the technical guts of how they achieve this certainty. We're going to unpack the math behind this formalization, focusing on these things called knowledge projections. We'll analyze the agentic expansion mechanism, specifically their layer-wise expansion strategy, and we'll look at the empirical results that back all this up, because the numbers are pretty compelling. We're talking state-of-the-art performance among open-source IS agents on tough benchmarks like GAIA and WebWalkerQA. They're often getting over 60% accuracy on GAIA, which is, well, really impressive for open source. Okay, let's make this concrete. The paper has a nice figure 2, contrasting these two approaches. We've got the old way, information-driven 2A, and the new formalization-driven way, 2B.
Right. And the information-driven diagram clearly shows that flow. Raw data organized info structure LLM tries to map that to a reasoning structure, synthesized data. And like we said, the weak link, the really hard part, is that middle step. where the LLM is basically guessing at the intended logic based on noisy input. That's where the ambiguity and the tendency towards simple, repetitive data comes from.
So the agent ends up training on data that might have errors or fuzzy logic baked right in.
Yeah.
Whereas the WebShaper approach, 2B, it completely sidesteps that problematic inference step.
Exactly. Its flow is deductive. Formalization comes first. That formalization then guides the information collection, and that controlled collection process directly produces the synthesized data. The formal structure is the skeleton from the absolute start. And this design inherently guarantees much more consistent reasoning trajectories in the data. It also forces diversity because it's exploring the space of possible formal structures, not just scraping the surface of whatever content is easily found on the web.
Okay, so this structural guidance gives WebShaper some key advantages. The paper lists 3. Let's walk through them. First up, broader task coverage.
This comes directly from using math to define the problem space. By using parameters like relations, sets, and how they combine logically, they can systematically map out a huge variety of potential complex IS patterns. And crucially, this process isn't limited by what web pages they happen to find first. Traditional methods can only generate questions if the answer seems readily available in the content they've already scraped. WebShaper defines the potential multi-hop complexity first. It ensures the dataset covers a much richer, more diverse set of real reasoning challenges. It's more like designing the exam questions deliberately, rather than just finding questions people have already asked online.
And that ability to design the structure leads right into the second advantage, task controllability. If you define it formally, you can dial the difficulty up or down precisely.
Absolutely. Those parameters in the set theory language, like how many intersections are needed, how deep the nesting goes, which specific relations are involved, they give you fine-grained control. You can specify exactly the kind of reasoning structure you want the agent to learn. For instance, the framework lets the creator's mandate say, this task must involve exactly 3 hops, or it must use a combination of union and intersection logic. You just can't get that level of precision when you're working backwards from messy web text.
And the third advantage, maybe the most critical one, is that this mathematical rigor tackles that initial problem head-on, structural and answer consistency.
Yes, this is arguably the biggest practical win. Those formal representations, the set theory stuff we're about to get into, they are inherently interpretable, mathematically verifiable. So when the whole system, from expansion to search to synthesis, is forced to align with this predefined, logically sound, set theoretic structure, the chances of getting inconsistencies between the reasoning steps and the final answer just plummets. Compare that to the old way, where an LLM is trying to figure out the logic from a paragraph. It's so easy for small hallucinations or logical flaws to creep in and corrupt the training signal. WebShaper uses a ground truth that's derived directly from the math. It's much cleaner.
All right, let's get into that mathematical core. How exactly do they formalize information seeking using set theory? For our audience who are comfortable with this level of detail, let's start with the basic building blocks, the universal set and the relation space.
Okay, so first we define $. This is just the universal set of absolutely all entities we might care about. It could be anything, a player's name, a team, a year, a city, a concept, everything. Then we define trual. Trual represents the specific relation between entities. Formally, it's a subset of $. Times IA, the set of all possible pairs of entities. So if we have a relation like born in, truals would contain pairs like person A, city X, person B, year Y, and so on.
Okay, universal set E relation R. And these combine to form the fundamental unit of their framework, the knowledge projection, or KP.
That's right. The KP is really the workhorse here. Mathematically, it's defined in equation 2 as VEV in V in our text. What does this mean conceptually? You start with a set of entities, VS. The KP operation projects this set via dollars through the relations dollars. The result is a new set of entities where each dollars is related via D dollars to at least one entity that was already in your starting set V dollar.
Think of it as a structured way to retrieve related information.
Can you give a quick example? Like, how would we use a KP to find, say, everyone born in the 90s? Sure. Let for be the born in relation. Let vor be the set containing all the years from 1990 to 1999, so 1990 and 91, 1999. Then applying the KP, or born in, would yield the set of all people 2L, such that there exists a year in the 90s, where bodies is in the born in relation. Basically, it formally retrieves everyone born in that decade. It turns retrieval goal into a precise mathematical operation.
Okay, that's the basic unit. But the real power seems to come from combining these KPs to handle complex, multi-step reasoning. There are 2 main ways they combine them, R union and intersection. Let's start with R union.
Right. Our union, denoted with the standard union symbol, the kept dios. This is used when the task involves or-are conditions, or finding things related to a broader set of possibilities. Think about range queries, like finding players active between 2000 and 2010 inclusive, or situations with uncertainty. Formally, it looks like RS1 cup or RS2 cup, RSMLSS. The final set or set includes any entity related via to any of the initial sets, 2 us and dios up to $7.
Okay, and this brings us to something the paper highlights as crucial. Proposition 1, the distributive law. They prove that Tritus 1 cup is exactly the same set as Tritus 1 cup S2 law. Why is proving this mathematical equivalence so important for actually building and running the agent? Seems like a small detail.
But it's a huge detail for implementation and efficiency. That's the key insight. Imagine, without Prop 1, if your task was find all papers published between 2015 and 2019. That's 5 years. The agent would theoretically need to manage 5 separate KP objects, and then after computing those 5 result sets, it would have to perform the set union operation on them explicitly. The complexity of the agent's internal state, what it needs to keep track of, just explodes as the range gets wider.
Right, scales linearly with the number of items in the OR condition.
Exactly. Proposition 1 provides a massive simplification, because the union of the results is the same as the projection on the union of the inputs. The agent can just create one big input set first. Valea, S2 cup, SM up. In our example, Valai dollars, $15, 2016, 2018, 2019, and then it performs only a single knowledge projection, $8 This drastically cuts down the complexity. Representing these OR conditions or range queries becomes much, much easier for the agent to handle in its prompt and its internal state management. Huge computational win.
That makes perfect sense. Consolidation for efficiency. Okay, what about the second operation? Intersection.
Intersection, kappa file, is for the A and D conditions. When the target entity has to satisfy multiple criteria simultaneously, often involving different relations. Equation 4 defines it. Cup 8, cup U, cup 2 SD. So as the dollars shade it to cup beyond cup UR. So if you want, say, players who played for Team X and also won an award, TSA2, the result is only those entities that are in both result sets. This is how you implement multi-criteria filtering and constrain the search space in complex IS tasks.
So putting it all together, these KPs and the union intersection operations define the final target set, T, often recursively. This gives the full task blueprint.
That's right. The general definition, equations 5 and 6, shows that the target set T dollar can be quite complex. It might be an intersection of several KPs, TT equals R1 T1, cap R2 T2, cap dots, cap RKT, and critically, the input to one KP, like T dollar, might itself be the result of another nested KP calculation. It's recursive. The actual information-seeking task is then simply defined as 2T dollar, which just means find the entities in the set T.
Okay, this is getting complex, but in a good structured way. Let's really cement this by walking through that detailed example from the paper, equation 8. This shows how a pretty convoluted natural language question gets precisely mapped onto this formal structure.
Yeah, it's a great example. The question is, which player of a team in the 2004-05 season who was born in 90s? This team is founded in 1966 and is an East German football team. Okay, lots going on here. We've got a time range, 2004-05 season, multiple conditions on the player born in 90s, but also a nested condition defining the team itself, founded in 1966, East German football team.
Let's break it down. Start with that nested part, finding the team first. Let's call that intermediate target T dollars then.
Okay. So T$1, the set of relevant teams, must satisfy 2 conditions simultaneously. That means intersection. Condition 1, the team is related via Lyle to the entity, 1966 dollar. The team is related via water the entity to dollars on, $dollars and text T dollar. This tells the agent, step 1 is to figure out this set of teams, $dollars ons.
Got it. Now for the main target, T dollars, the set of players. This seems to be an intersection of 3 different constraints.
That's right. 3 things must be true about the player. Constraint 1. The player must be related via the team set T dollar we just defined, so R text plane T1. Constraint 2. The player must be related via R to the season. This is the temporal range 2004-05. Using our R union simplification, Prop 1, this becomes, to talk up here, we combine the years first. Constraint 3, the player must be related via R text born in to the 90s. Again, this is an R union over all years, 1990 to 1999. So, big copy, which simplifies via Prop 1 to R text born in 9.
Okay, and the final answer, the set of players' dollars, is the intersection of all 3 of these complex conditions.
Exactly. Putting it all together. T copy 1, cap R text born 1, and T dollar. Where T1 itself is that intersection defining the team.
Wow. Okay, it's really something to see that natural language query, which feels intuitive but vague, translated to such a precise, almost algebraic statement. It really exposes the nested multi-level reasoning these agents need to perform. And having this formal map up front provides that clear, traceable path for complex reasoning, exactly what you'd want for creating really high-quality training signals, avoiding that ambiguity we talked about earlier. Okay, so we have this powerful mathematical blueprint for defining complex tasks. But how do they actually use this to generate tons of high-quality training examples? It starts with phase one, seed question construction, getting some diverse, non-trivial starting points, right? Q$T data.
Precisely. You need a good base to build upon. What they did was compile an offline snapshot of Wikipedia. And critically, they made sure to preserve all the internal hyperlinks, because those links represent the initial set of relations, the $20 space they can work with. Then they performed random walks, starting from different pages, following these links, and collecting the content along the way. An LLM was then prompted to generate an initial question-answer pair, but, and this is key, grounded only in the specific content collected during that random walk.
So they prevent the LM from just using its own baked-in knowledge at this stage. It has to stick to the provided text from the walk.
Exactly. It minimizes hallucination right at the seed stage.
Yep.
But, even with grounding, you'll still get some noise or maybe questions that are trivial. So they added a crucial validation step. They took each generated seed question and ran it through an existing agent framework, WebDancer, which uses the QWQ model. They ran 5 attempts, 5 rollouts for each seed question. And they only kept the seed questions where WebDancer managed to find the correct answer in at least one of those 5 tries. This filtering was pretty strict. It resulted in about 18,000 seed questions being kept. It ensures the starting points are actually solvable by an agent, but also not completely trivial.
Okay, 18,000 validated non-trivial seeds.
Yeah.
Now we get to the really innovative part, phase 2, agentic expansion, one come plus cheat. The goal here is to take these seeds and progressively make them more complex, adding more reasoning steps, but always staying true to that formal mathematical structure we discussed. And the core engine for this is called the expander.
Right. And the first challenge here is practical. We have this nice but complex recursive set theory notation from section 2, but you can't just feed that raw mathematical notation directly into an LLM prompt for expansion. It needs a more linearized, agent-friendly format.
Okay, so let's detail this KP representation they designed for the agent prompt. How does it work?
They broke it down into 3 simple building blocks. First, constants. These represent specific entity sets, like C at 90s or C at East German football team. The epsilon symbol just separates the type identifier from the description. Second, variables. These are placeholders for the results of KP operations, like V at X or V at Y. They represent the sets the agent needs to figure out. And third, the core unit. The KP triplet. This looks like $6 are $6. Your $6 is the target variable, the result set. True dollars is the relation being applied, and Zello dollars is the source set, which could be a constant or another variable.
Okay, simple enough. But how does this triplet system handle that complex recursion and composition we saw in the big example, like R$, R2S?
It flattens it using intermediate variables. So R$, R2SS wouldn't be nested. Instead, it becomes a list of 2 triplets that chain the operations together. You'd have something like 1 all at Y, R2, S, V at X, R1, V at Y. See how the output variable V at Y of the first triplet becomes the input source for the second triplet. And intersections, they're handled implicitly. If multiple triplets have the same target variable, say V at X, it implies an intersection of their results is needed to get the final V at X. For that really complex team player example from before, equation 8, the full formalization gets flattened into a list of 5 such triplets, shown in equation 10 in the paper. This list explicitly spells out the sequence of relational steps and the implied intersections needed to get the final answer T. It's a linearized plan.
That's clever. A flat structure that encodes the full dependency graph. Okay, so with this representation in hand, they can implement the layer-wise expansion strategy, LWES. This sounds like where they really control the growth of complexity, making sure it gets deeper, not just wider or messier.
Exactly. LWES is the architectural constraint that ensures meaningful, structured growth in task complexity. If you think of the task structure, the dependencies between these triplets, as a graph. Previous attempts at automatic expansion often fell into 2 traps. One was creating random structures, just tacking on new KPs randomly. This often led to redundant steps or, frankly, nonsensical connections, like trying to relate two constants directly. The other trap was sequential structures. This often created reasoning shortcuts. For example, a newly added constant might connect directly to the final target variable, letting the agent skip all the intermediate steps they actually wanted it to learn.
Ah, so the task looks complex on paper with more triplets, but the agent finds an easy way out, like a single lookup, bypassing the intended multi-hop logic.
Yeah.
LWES is designed to prevent that.
Precisely. LWES maintains a strict layered structure. The strategy involves traversing the current task graph layer by layer from the final answer node outwards. It identifies the current leaf constant, those constants that are inputs at the deepest points of the existing structure. The expander agent's job is then to replace one of these leaf constants with a new variable node. This new variable node then becomes the target of one or more newly generated KP triplets. The original constant becomes the answer to this new subproblem. By always expanding at the leaves, LWES ensures two things. One, it minimizes redundancy because you're always adding depth at the periphery. Two, it prevents those shortcuts because the core path from the original inputs to the final answer is always preserved and just gets longer layer by layer. The complexity grows in a controlled, incremental way. The number of layers in seal becomes a direct measure of the task's reasoning depth.
Okay, that's a very structured approach, but I have to ask, does forcing the strict layer-by-layer structure risk making the training data too artificial? Real-world information seeking can be messy, unpredictable. Does this rigid structure potentially sacrifice the ability to handle that real-world noise? Is structure always better than organic complexity for training?
That is a really important question. And the paper's results and the general thinking here strongly suggest that for training, especially in the initial SFT and RL phases, this kind of controlled, structured complexity is actually superior. Yes, real-world tasks are messy, but training data needs to provide clear, unambiguous learning signals. The rigidity of LWES guarantees that if a task is defined by the formalization as requiring, say, 3 specific logical steps in 2 intersections, the agent must learn to perform those steps and intersections to get the reward. There's no easy way out. This forces the agent to master the underlying structural logic and the required multi-step tool coordination. These are fundamental transferable skills. And the evidence, like the strong performance on the messy real-world GAI benchmark, suggests that agents trained on this rigorous structured data actually generalize better to handling unstructured tasks later on.
Okay, that makes a lot of sense. You need to learn the rules perfectly before you can handle situations where the rules seem bent or broken. Learn the structure first. So let's move to phase 3. The expander agent itself. It's built on the React framework, thought, action, observation cycles. What specific tools does this expander agent have to actually perform this formalization-guided expansion?
It's equipped with 3 key tools designed specifically for this job, integrating that formal structure with actually interacting with the world, or at least the web. First, it has a pretty standard search tool. This uses Google Search, and importantly, it supports not just queries, but also temporal filtering based on years. The parameters are cathlivis, text queries filter year. This is how it grounds the expansion in real-world information needed to resolve constants or find entities for new subproblems.
Okay, standard search. The second tool, summarize, sounds like it's directly implementing that R-union simplification we discussed earlier, proposition 1.
That's exactly what it's for. The summarize tool is the computational counterpart to the distributive law for R-unions. When the formalization requires finding entities related to multiple items, like players active across several years, the search tool might return multiple URLs. The summarize tool takes these URLs, processes the content based on a specified goal, what kind of information to extract, aggregates it, and critically outputs a single unified constant set representing foo-r S1, S2, and NS. This completely avoids the need for the agent to juggle multiple parallel KP results for OR conditions, keeping the state manageable, just like Prop 1 allows mathematically.
Very neat. And the third tool, validate, sounds like the quality control mechanism, making sure the expansion stays consistent and actually adds complexity.
Yes, validate is the enforcer. It uses another model, the QWQ model from WebDancer, to perform 2 crucial checks, both guided by the formalization. Check number 1, consistency. It verifies if the sub-question the expander wants to create and the constant it aims to replace actually match the type required by the formal structure. For example, if the formalization graph expects a date at a certain node, validate checks that the new subproblem doesn't try to find a person's name instead. This prevents logical breaks in the chain. Check number 2, simplicity. This is really important. It checks if the newly proposed sub-question is actually too easy. If the QWQ model can just answer this new sub-question directly, maybe with a single search, without needing the multi-hop reasoning the expansion was intended to create, then the expansion is rejected. This ensures that every successful expansion genuinely increases the required reasoning depth. It doesn't just add trivial steps.
Okay, so that's how the complex validated questions get synthesized. Then phase 4 is about actually generating the full trajectory for solving these questions and training the final agent.
Right. Once a complex question, do SBO plus 1T, is successfully generated and validated by the expander, they use agents based on QWQ to actually solve it. These agents use the standard search and visit tools within the React framework to generate the step-by-step solution path, the trajectory. They run 5 attempts, rollouts per question, but raw trajectories can still be noisy. So they apply more filters here. First, correctness. They use a separate judge LLM to check if the final answer is right. They also filter out trajectories that had obvious tool execution errors. Second, quality. This filter looks for things like hallucinations within the reasoning steps or excessive, unhelpful repetition. After all this filtering, they end up with a data set of about 5,000 high-quality, complex, validated trajectories.
5,000 trajectories. And the training itself is a two-stage process. Supervised fine-tuning, SFT first, then reinforcement learning, RL. Let's dig into that SFT stage. They use something called mask loss, equation 12. Why is masking important here? What are they masking?
The mask loss is critical for SFT in these agent scenarios. They mask the loss calculation over the observation tokens in the trajectory. Remember, React is thought action observation. The observation is the raw text returned by a tool, like the search result snippet or the content of a visited web page. By masking the loss on these tokens, they ensure the model is primarily learning to predict the thought and action steps. It forces the model to optimize its internal reasoning process and its decisions about which tool to use next, rather than just learning to copy or predict the text it retrieved from the web. Without masking, there's a big risk the LLM just becomes a really good summarizer or paraphraser of the observations without actually learning the strategic multi-step reasoning policy needed for complex IS.
Got it. Focus the learning signal on the agent's decisions, not just the retrieved content. Okay, so SFT sets a baseline policy. Then they use RL, specifically the GRPO algorithm, Generalized Policy Optimization, EQ13. For our listeners familiar with RL techniques, why GRPO? Why not something more standard, perhaps, like PPO? What's the advantage here?
GRPO is a smart choice for these kinds of tasks. Complex information seeking involves. Together, these make GRPO much more robust and effective for optimizing policies for the kind of deep, multi-step reasoning tasks generated by WebShaper.
Okay, we've been through the theory, the math, the engineering of the data synthesis. It all sounds incredibly rigorous. Now let's see if this rigor actually pays off in terms of agent performance. The paper makes some strong claims about state-of-the-art results, especially on GAIA and WebWalkerQA.
Yes, and it's worth quickly mentioning why those benchmarks matter, particularly GAIA. GAIA, the General AI Assistant benchmark, is notoriously difficult. It was specifically designed by researchers at Meta and Hugging Face to test capabilities that require complex, multi-step reasoning, often involving multiple tools, and aiming for what they call level 4 or level 5 human-level intelligence. Doing well on GAIA is considered a strong indicator of genuine autonomous reasoning, not just good retrieval. And WebShaper really shines here. It achieved the best results among all published open-source IS agents on both GAIA and WebWalkerQA at the time of publication. Specifically, the configuration using WebShaper data to train the Kuan 2.572b model hit an average pass at one score of 60.1% on GAIA. Now, 60.1 might not sound like 90%, but on GAIA, that's a huge achievement for an open source model. It significantly outperformed the next best open source competitor, WebSailor, by about 4.7 percentage points. And maybe more impressively, it brings the open source performance remarkably close to the reported score for OpenAI's closed source deep research agent, which was around 67.4%. That's closing a significant gap. Plus, the paper shows the WebShaper dataset provides consistent benefits across different backbone models, Qwen32b, Qwen72b, QWQ32b, proving the data itself is powerful.
That 60% on GAIA is indeed a big number for open source. And this success is attributed directly to the quality of the synthesized data. Let's look at the direct comparison, the validation of the synthesis data shown in Table 2, where they train the same models on different datasets.
Right. This is the head-to-head test of the data generation method itself. They took the same base models, Qwen32b, 72b, QW232b, and fine-tuned them separately using SFT on WebShaper data versus other popular IS data sets like the original WebWalkerQA, E2HQA, and MHQA, which were built using more traditional information-driven methods. The results are pretty clear-cut. Across all tested models and benchmarks, training on WebShaper data led to consistently better downstream performance. For instance, using the QWQ32 model, WebShaper data yielded an average score of 53.3, while the next best, WebWalkerQA and E2HQA, only reached 45.6. This really drives home the point that the formalization-driven approach produces a cleaner, more effective, and structurally more demanding training signal compared to prior methods.
Okay, strong overall results. The ablation studies then drill down into why it works, validating those specific design choices we discussed. First, they compared using the formalization language, FL, for expansion, versus trying to do it with just natural language, NL prompts.
Yes, this ablation directly tests the core idea. Is the mathematical formalism itself necessary, or could you get similar results just by carefully prompting an LLM in natural language to increase complexity? The results were stark. When they replaced the set-theoretic triplet representation with a version where the expander agent tried to manage and increase complexity using only natural language instructions, performance dropped significantly. The formalization language FL variant consistently and substantially outperformed the natural language NL variant on all models. This really confirms two things. One, the formal structure seems better at systematically generating a diverse range of complex task types. Two, and maybe more importantly, the precision of the mathematical notation drastically reduces ambiguity and the potential for error propagation during the automated expansion process. Natural language just leaves too much room for the LLM expander to misunderstand or generate flawed structures.
Precision matters. And the second key ablation looked at the expansion strategy. Layer-wise expansion, LWES, versus a simpler sequential structure.
Right. This tests whether that specific LWES strategy, expanding only at the leaves, is truly better than just adding new steps sequentially. And again, the results support the design choice. LWES performed measurably better than the sequential variant across all the base models they tested. This backs up our earlier discussion. LWES appears successful at its goal of preventing those reasoning shortcuts and avoiding redundant complexity. By forcing expansion layer by layer from the leaves, it ensures that added complexity is meaningful complexity. It forces the agent to learn a genuinely deeper reasoning chain, not just find a clever bypass.
So the formalization works, and the LWES strategy works. To really see the effect of this on the kinds of tasks generated, we need to look at the tool call analysis in Figure 8. This quantifies how often and how deeply the agents actually needed to use tools like search and visit to solve the task created by WebShaper versus other datasets.
Exactly. This is where you see the downstream impact of that structural rigor during synthesis. It translates directly into more demanding agent behavior during execution. When you compare the distribution of tool calls for tasks from WebShaper versus baselines like E2HQA and MHQA, the difference is quite dramatic. WebShaper tasks force much heavier tool usage.
Can you give some specifics on the search complexity?
Sure. The analysis shows that the proportion of tasks requiring more than 3 separate search operations is 3 to 4 times higher for WebShaper data compared to the baselines. This clearly shows these tasks aren't solvable with just 1 or 2 simple lookups. They demand iterative searching, refining queries, potentially searching based on the results of previous searches, that genuine multi-hop information gathering process.
And does that pattern hold for navigating web pages, the visit tool?
It does. The distribution for visit calls also shows a much heavier tail for WebShaper. A significantly higher ratio of trajectories require more than 10-page visits, whereas the baseline datasets see that frequency drop off much faster. This suggests the tasks require agents to navigate more deeply, process information from multiple sources, and synthesize findings across different pages, reflecting more complex real-world research scenarios.
Okay, more searches, more visits. And finally, they looked at the total number of tool calls per trajectory, representing the overall composite reasoning complexity.
Yeah, this sums it all up. WebShaper roughly doubles the number of tasks requiring more than 3 tool calls in total compared to the baselines. But what's really striking is the tail. WebShaper maintains a non-trivial proportion of tasks requiring up to 30 total tool calls, whereas the others fizzle out much earlier. This is the direct payoff from the LWES strategy preventing shortcuts. The underlying formal structure, when expanded layer by layer, necessitates this high frequency of tool interaction to reach the solution. It's strong evidence that the WebShaper method successfully synthesizes tasks demanding a level of compositional reasoning and execution complexity far beyond what previous open-source datasets offered. It forces the agent to become proficient at complex, extended tool use. Hashtag #OutReactualAge.
So let's try to synthesize all of this. It really feels like WebShaper marks a significant shift, doesn't it? We're moving away from this reactive approach of finding information and then trying to impose structure on it, towards a much more proactive approach, defining the desired reasoning structure first, using formal mathematics, and letting that structure guide the entire data generation process.
Absolutely. I think the core contribution here is twofold. First, introducing that rigorous set theory formalization using knowledge projections, R-union, intersection as the language for defining complex IS tasks. And second, coupling that with a highly controlled, disciplined expansion mechanism, the layer-wise expansion strategy. It's this combination that yields training data with demonstrably superior quality and structural complexity, especially for the open source world. And that data quality is what allows models like Kuan 2.572b to reach these new performance milestones, getting much closer to the capabilities of proprietary systems on really challenging benchmarks like GAIA.
And the implications seem pretty broad. If you can formalize tasks independently of messy human data, you can potentially engineer training environments that push beyond human capabilities.
That's a fascinating possibility. It opens the door to systematically creating training data for tasks that require reasoning complexity or depth that might be rare or non-existent in typical human-generated examples. Think about highly complex scientific modeling, maybe discovering new mathematical proofs or analyzing incredibly intricate systems. And because the formalization abstracts the structure of the task away from the specific domain entities, agents trained on this data might develop stronger generalization capabilities. They learn the fundamental logic of multi-hop reasoning, which could potentially transfer better across different domains and task types.
It really hammers home this idea of using mathematics not just to analyze AI systems, but to actually design the challenges we set for them. Set theory worked incredibly well here for web-based information seeking. So maybe the final thought for you, our listener, to ponder is this. Where else in AI could we benefit from using formal mathematical structures as the initial blueprint for defining a task? Beyond the obvious areas like theorem proving or knowledge graph QA, could this proactive formalization-first approach be applied to other complex domains, like planning or creative generation, or even social interaction modeling? Could defining the structure mathematically upfront be the key to unlocking the next level of robust general AI capabilities? Something to think about.